For decades, we've basically been conditioned to think that space exploration is this super exclusive club, right? We picture massive government agencies, multi-billion-dollar budgets, and rockets literally the size of skyscrapers. But what if I told you that the space race has fundamentally changed? What if the next great orbital mission isn't being built in some top-secret government hangar, but on a student's desk or by a small group of open-source enthusiasts? Welcome to our explainer on CubeSats and the DIY space revolution, where we're going to look at how the cosmos was finally democratized.
All right, let's dive right into this. The entire democratization of space doesn't actually start with some massive technological leap in rocket propulsion. It starts with a simple rule, and a cube just 10 centimeters across. I mean, think about that for a second. 10 centimeters. That's literally the size of a Rubik's Cube. Yet, this tiny little form factor has completely shattered the financial and logistical barriers of reaching low Earth orbit.
So here's our flight plan from today. We're breaking this down into 6 parts. The 10-centimeter revolution, what's actually inside a CubeSat, the cost comparison of students versus corporations, communicating with satellites, orbits and visuals, and finally, exactly how you can join the mission.
Starting with Part 1, the 10-centimeter revolution. Welcome to the DIY space era.
So the secret weapon of the CubeSat isn't just its tiny size, it's the modularity. This 10-centimeter cube is known in the industry as a 1U, or 1 unit. You can really just think of these like high-tech Lego blocks. You can stack them. If your mission needs a bigger lens for a camera, you just stack 3 of them together to make a 3U, which ends up being roughly the size of a loaf of bread. Need to pack in a complex laser communication system? You can scale right up to a 6U or even a 12U. And because the sizing is totally standardized, they don't even need their own rockets. They just catch rides as passengers, tucked right into the spare space alongside massive traditional satellites.
Moving on to Part 2. What's inside a CubeSat? Let's talk commercial parts.
So what exactly is packed inside these orbital bread boxes? Well, it's astonishingly similar to building a custom gaming PC, and it brilliantly illustrates exactly why the barrier to entry has absolutely plummeted. You don't necessarily need million-dollar radiation-hardened custom chips anymore. A lot of modern CubeSats just rely on COTS, commercial off-the-shelf components. You've got an onboard computer acting as the brain, solar panels basically glued to the sides, a basic radio, and an orientation system just so the satellite doesn't tumble wildly out in the void. And for the payload, it could be anything from a scientific spectrometer to an off-the-shelf camera module. You can literally just buy certified parts from online space supermarkets. It's incredible. Now, building one of these usually takes anywhere from 6 to 24 months. You design your power budgets, assemble all the parts in a clean room, and navigate the tricky radio licensing so you don't accidentally step on anyone else's frequencies. But I want to highlight step 3 here, testing. This is the ultimate trial by fire. Because look, before anyone is going to let your tiny box onto a multi-million-dollar rocket, it has to survive the shake table, which simulates the violent vibrations of a launch, and the thermal vacuum chamber, to prove it absolutely won't fry in the raw sun or freeze when it hits the Earth's shadow.
Which brings us to Part 3, price. It's students versus corporations, and the true cost of orbit.
Let's talk about the economics of space, because we have a fascinating contrast here. On the high end, a 12U Rolls-Royce satellite built for a major corporation might cost upwards of $3 million. I mean, it's packed with laser communications, edge AI processors, cold plasma thrusters, the whole shebang. But look over at the student version, an $85,000 1U satellite. It uses standard industrial microcontrollers, a basic UHF/VHF radio, and static solar panels. And what's amazing is that this student satellite will survive in orbit just fine. Plus, get this, if a university wins a launch grant from NASA or the ESA, that $50,000 launch cost completely vanishes. The actual hardware cost drops down to maybe 25 or 30 grand. That is roughly the price of a used car.
And knowing how cheap this is getting brings up a rather provocative question. If space is suddenly full of these highly accessible, relatively inexpensive gadgets, can you, sitting at your desk right now, intercept photos or data from someone else's satellite? Well, the short answer is absolutely yes.
Let's explore that in Part 4, communicating with space.
So, while commercial satellites from big companies like Planet or SpaceX use heavily encrypted feeds, there are plenty of open satellites, like NOAA weather satellites, that actually broadcast unencrypted images of the Earth every single day. But you can't just casually ping them anytime you want. You only have this narrow 10-minute visibility window as it flies over your horizon at a screaming 8 kilometers per second.
And to pull this off, you actually have to battle the massive Doppler effect, where the radio frequency literally shifts as the satellite zips past you. But you really can catch these downlink signals with a simple $30 software-defined radio, or SDR, plugged straight into your laptop. You just receive the photos in tiny chunked data packets to prevent any data loss.
Moving into Part 5, Orbits and Visualization, tracking everything in real time.
Now, keep in mind, these tiny marvels are not up there forever. They are constantly fighting atmospheric drag because, there's no hard, solid border where the Earth's atmosphere just stops, so low-orbit satellites are constantly rubbing against highly rarefied air. At 400 kilometers up, which is the height of the ISS, a satellite might only last a year before burning up. The real sweet spot is 500 to 600 kilometers, giving you a solid lifespan of 5 to 15 years. And notice how anything higher pushes into decades. Actually, there is a strict international 25-year rule. Satellites must deorbit within 25 years of their mission ending. That's absolutely crucial to prevent a catastrophic buildup of space debris. Because of this, many of these CubeSats are placed in a very specific, calculated path called the Sun Synchronous Orbit. Think of this as essentially a cheat code for climate scientists. Because the satellite flies pole to pole while the Earth rotates underneath it, it eventually scans the entire globe. But the crucial part is that it passes over locations at the exact same local solar time every single day. This means the shadows on glaciers or forests are identical day after day, which makes it incredibly easy to spot environmental changes over time.
So how do we actually track them? Well, the data to calculate exactly where any given satellite is at any given second is completely open source. It's maintained by the U.S. Space Command in the form of coordinates called TLE strings. A tech enthusiast can literally just use a simple Python script with a library called Skyfield, store the calculations in a standard database, and push the data to a front-end map to build their own live tracking dashboard.
So the real choice here is how you want to experience this data. Do you want practical utility? If so, you can set up Telegram webhooks so your phone buzzes the exact second a weather satellite is overhead, telling you, hey, point your antenna at the sky right now. Or do you want the visual wow factor? By using rendering libraries like Cesium.js, you can create a 3D digital twin of the Earth right in your browser. You can sit there and watch a live 3D model of a CubeSat fly over your virtual house, while its solar panels dynamically light up based on the actual real-time position of the sun. It's so cool.
Which brings us to our final section, Part 6, How to Join the Mission, Entering the DIY Ecosystem.
We've covered a lot of ground today, from hardware down to orbital mechanics. But how can you actually step into this ecosystem right now? Honestly, the barrier to entry has truly vanished. If you want to talk hardware or figure out regulations, communities like Reddit's r/CubeSat are just buzzing with actual NASA engineers chatting with university students. Want to receive data? You can join SatNogs, which is an amazing global network of volunteer antennas. If you build a little ground station and hook it up to their network, you can access live telemetry from amateur CubeSats passing over Tokyo or Paris in real time. And over on Telegram, channels like R4UAB are filled with radio amateurs posting daily logs of satellite signals they've caught right from their own backyards.
The cosmos is no longer locked behind gates of billion-dollar funding. The tools, the open data, the affordable hardware, and this massive, passionate community are all out in the open, waiting for you. You can download open-source orbital data today, grab a $30 radio receiver, and literally listen to spacecraft passing over your roof tonight. Or, hey, maybe you'll start designing your very own 1U satellite. The blueprint is right there. So my final question to you is, which part of the space revolution will you build from your desk today? Thank you so much for tuning into this explainer, and keep looking up.